All right. So, welcome everybody. I am going to talk about how to prevent the robot uprising today. I specifically want to introduce a safe reinforcement learning architecture that is based on Model Predictive Control. I will be using MPC as a shorthand for Model Predictive Control and RL for reinforcement learning because it is a mouthful. In the beginning, I do want to manage some expectations, though. I am not here to talk about Terminators. I am also not here to talk about Skynet. We're mostly going to talk about math and architectures in order to facilitate reinforcement learning while in keeping with our safety standards that we want to match. In the beginning, I want to talk about myself first. I am that idiot on stage. Yeah, exactly. I am also called Neo. I am a robotics enthusiast. I also did robotics for my bachelor's. I did that at the University of Lübeck. A lot of the stuff I'm going to talk about today is my bachelor thesis and the research going on at the robotics research group in Lübeck. I have pivoted since then in my master's degree towards cybersecurity and am now a cybersecurity engineer for my job. So robotics has become more of a hobby at this point. I still really like to talk about it, and cybersecurity for robotics is also a very interesting field in the industrial applications. There's a lot of stuff that you can do there, that might just be a topic for a future talk. What are we going to do today? We want to create a framework for us to use reinforcement learning or machine learning for safety critical applications. I'm going to introduce all of those things later. Don't worry if you don't get all of the terminology at this point. Why do we want to do that? We have some applications where we would really like to use machine learning, some problems that are complex that we don't want to program anything for, and we just want our computer to learn how to solve our task. That is quite easy for some things that we can easily simulate, things that are not safety critical, where we can just throw away our system if something goes wrong. It is not very easy for safety critical applications, but we still want to do it. There are ways to do that. Some of the applications that this might be really useful for is robots. Safety critical applications. Applications where something can be damaged, somebody can be killed, somebody can be hurt, or a large amount of property or IP damage can be a consequence of a failure. Robots are a prime example of that. Basically, any physical system that interacts with humans or the environment is some sort of safety critical system, because you don't want a self-driving car to run you over, you don't want the robot in your house to slap you across the face, and you don't want whatever automatic system is inside your plane to press the self-destruct button. We're going to do some definitions at this point because I need to get them out of the way in order for you to get the rest. We're going to proceed with Model Predictive Control, the heart of the thing I'm going to talk about today. This is the Wikipedia definition. Model Predictive Control is an advanced method of process control that is used to control a process while satisfying a set of constraints. That is an explanation that is useful to absolutely nobody because it doesn't say anything. I am going to explain it a bit further. What is a system? A system is something that takes an input, a control input, and outputs some sort of state into the world, some sort of interaction with the environment. We define our system like this. This is a dynamic bicycle, kinematic bicycle model. It is used, it is heavily inspired by real-world bicycles. It is used to approximate cars in a lot of research, for example, this one. Hi. This is relatively simple. It is complex enough in order to grasp all of the concepts. It is still a rough approximation of the real world. So that is why I'm going to explain this one in a bit more detail. This system has some variables attached to it. We have our states, so our x and y position. We have our yaw angle and our side slip angle. You can see those here in the diagram as well. Those describe how the system currently is, the current state of what we have, what we do, where we are, how our system looks. We also have some parameters. The length of the distance between the tires, all of that jazz. In a robot, it would be how long is the arm, how heavy is the system, all the things that basically do not change. Those are just parameters. Those get thrown into the math later on. What those are doesn't really matter. We also have some control inputs. Those are important because that's the one our system can actually control and do something with. The one our model predictive control can control. These affect all of these state variables in a way that is described through the dynamic model. You don't need to grasp all of this math, by the way. That is just here for completeness. Don't worry if you don't get how that actually calculates anything here. It is mainly important that you get that this describes how those state variables change. That is wonderful. It is also not new. A lot of control algorithms can work with this. The thing about model predictive control is that it can account for constraints in your system. You can tell it that you don't want x to be higher than 10. You can tell it that you can only steer in a certain angle. You can tell it your maximum acceleration or your maximum braking rate. You can tell it basically whatever constraint you can somehow put into math. You can get creative there. It has a lot of possibilities. It is also able to look into the future. Like this. This is a curve of what variables the model predictive control has access to and is going to output. We are currently at time step k, and we want to calculate for our goal, for our reference trajectory that we want to follow, what control inputs we need to take in order to closely track that. At point k, a model predictive control algorithm will calculate all of these, all of them, at the same time at time step k. It will do so again at k1 and k2, but at k it looks into the future and sees what is going to be happening. And it does not only predict its own control input, it will also predict its own output, so the output of the dynamic system that it controls. That is important because it allows us to make assumptions about our future state. And it allows us to verify that our constraints that we have put into the system, we don't want x to be higher than 10, will be kept in the future. That one is going to be important. At this point, when I first held this talk in a test run, some confusion came up about the different models I'm talking about. A system model is the model of the system that we control, our car, or robot, or whatever we're doing. Model predictive control was originally invented to control chemical processes and power plants and all of that stuff. It has now found application in robotics, which is quite new. Our environment model is everything outside of the system that we control. The walls of the area around us, the floor, whatever else you could interact with the environment and can mathematically describe. For example, you could describe a wall as just a line in your environment, and you can calculate the distance to your wall. Then we also have a task model. Whatever thing we're actually trying to solve, get the car somewhere, get our robot to pick up a cup, some mathematical description of what we want to do. You could interpret this as part of the environment, but for our matters, it is easier to look at it as a separate thing. Okay. Dry part. Let's get into memes, because this is just too dry for me and I want to do something funny here. We have our model predictive control. It is very robust, it is strong, it can look into the future, it can do all sort of jazz. And now we give it a problem. We have our car that is running with some velocity towards a wall, and it wants to get here. That is its defined goal. Get to this point. The model predictive control algorithm is going to see this and going to see that maybe we should not run into a wall. Maybe we have some sort of constraint that tells us if wall, then don't. And that is not hard. It can look into the future, calculate its steering angle and its amount of acceleration, and just veer around the wall. No issue, easy. What happens now? This is where we quite literally run into issues. The issue being the wall. At this point, a model predictive control algorithm is going to quite literally panic. It's going to start screaming, running through the room, and blow everything up around it. Actually, in most applications, your program is just going to throw an error and crash at this point, because this is something that should never happen in a system that is MPC controlled from the beginning. This should only ever happen if you misconfigured something or you started in this state. And this is going to be important for us later, because, well, we can catch the error. We can know if a state is unsafe, and this model predictive control algorithm cannot recover the system or keep its constraints or not blow up the building. Keep this in mind. Now I need to introduce reinforcement learning. I have, again, a useful to nobody definition here. You can have that one. I only just wanted to have that on the slides. We have a reinforcement learning model. We have our environment and our task that we're trying to solve. I assume that a lot of you had some first interaction with reinforcement learning before, so I'm going to go through this a little bit quicker. You have the model that interacts with the system somehow. It performs an action on the environment that affects the task. We can measure how well the task was solved, how fast we got towards solving the goal. The system gets some sort of reward. In most reinforcement learning applications, this is going to happen a bunch of times. With it gathered sets of experiences, it's going to calculate a lot of math, a lot of machine learning mumbo-jumbo that is totally unimportant at this point. Point is, it's learning. It's going to get better at what it does. At some point, if this trains for an infinite amount of time with an infinite amount of interactions with the environment, this will become optimal. So it will perfectly solve the task. That is just a baseline theory of reinforcement learning. If it goes towards infinity, that thing is going to become perfect at some point. Its task is always to maximize this reward. However we define that reward is what the system is going to learn later on. If we were rewarded for keeping away from walls, it's going to keep away from walls. If we were rewarded for blowing up the building, it's going to blow up the building. Point is, it doesn't know that from the beginning. In the beginning, it is just going to be a process of trial and error. Well, those of you who are really clever might have noticed that this is a problem when dealing with safety-critical applications. For those of you who don't know where the problem is at this point, it's there. This is an issue for us, because in safety-critical applications, this will kill somebody. This will blow up the building. This will run our car into a crowd. This will do something very bad, by definition of what a safety-critical system is. Trial and error is really, really stupid when dealing with safety-critical applications. Okay, quick summary of what we're looking at now. We have our model predictive control algorithm. It is provably correct when given an accurate model. It is insanely computationally expensive because you need to calculate all of the steps into the future and solve for the most optimal one. And you also need a mathematical model of your task. That is the one I described before, and is also not adaptable because it is very rigid. There is some research going into that, which is very interesting to look at, but is out of scope for the things I am talking about today. Reinforcement learning is wholly unreliable. It might just blow up your building. It might kill somebody. But it is very adaptable and needs no system whatever. You can just give that thing a reward signal and some controls to play with, and it's going to learn eventually. That is the fun part, the thing we want to leverage in the end. This one is the important part. It is also very cheap when trained. We don't really care about the computation aspect in safety-critical applications because compute is cheaper than life. Wonderful. This looks kind of good, doesn't it? We have one system that is reliable and one that is very correct, but is not adaptable, and the other one is adaptable. So how do we put this thing together? Well, we need to look at the task model for that. Because how do I mathematically describe the task that I want to solve in a reinforcement learning application? And I'm going to make this really easy for myself, because you don't. If you have a task that you can mathematically solve, you don't need the reinforcement learning. It's waste. It's a waste of compute then, because if you can describe your task that you want to solve mathematically, you can just use the model predictive control or any other control algorithm. There has been research into that for ages. You don't need that. You need reinforcement learning for tasks that you can't mathematically describe, that are so complex or so such a pain in the ass to describe that you want your system to learn them for you. What is, however, pretty easy is describing not driving into a wall, because you just say your distance to the wall needs to be higher than some minimal distance. You can also just very easily describe not driving off a cliff as your Z position needs to be higher than the floor. And you can very easily describe not pressing the self-destruct button as don't press the self-destruct button. This is easy. This is math. The model predictive control algorithm can work with that. No issue. Okay. Based on all the things I told you, we're going to build an architecture now. We're going to start with our reinforcement learning model, our environment, and our task. We're not going to apply the actions directly now because we want to keep everybody safe. So we're going to put our MPC into the middle. I will refer to this MPC as the supervisor sometimes, because that is the terminology used in research a lot of the times. Please forgive me if I mix it up sometimes. Thank you. We have our state from our environment that is given to both, and we have some reward signal from the task in the environment that is given to the reinforcement learning model. We don't need that for the MPC because the MPC doesn't care about it. Wonderful. At this point, we assume that our system starts in a safe state. The car is parked, the robot is standing, the building is not blown up, the self-destruct button is not pressed. Baseline. Let's see how the system works when everything is fine and dandy. Reinforcement learning model creates some sort of action, gives that to the model predictive control algorithm that is going to look into the future. What are we going to do in the future? What is going to happen? Can we create some sort of control inputs that keep the system safe? And it goes, yeah, fine, dandy, the wall is far away, we can do whatever we want here. Give that action to the environment, apply it to the task, everything fine, everything starts over. Now let's assume our reinforcement learning model messes up. It tries to press the self-destruct, it tries to drive into a wall, it tries to slap its owner across the face. Whatever. The MPC is going to panic at this point because it can't keep its constraints when given this action. What does the MPC do at this point? It defines our state as unstable but safe. We haven't done anything because this action has not been applied to the environment at this point. But a reinforcement learning agent should kind of get a notice that he messed up. So it's going to bonk it. It's going to hit it over the head with a baseball bat. Doesn't matter. It's going to give it some sort of reward signal that signals, buddy, you just messed up big time. Do not do that. Set the reward to 0, set it to -1000. Whatever, give it some sort of signal. This signal can be used to train the reinforcement learning model. It's going to override this reward if you configure the system correctly. At this point, we have an issue, because now, what happens? If we start over now, this state hasn't changed. The reinforcement learning model is still going to create some sort of faulty action. It might be less wrong this time, but it's still going to create some sort of faulty action. We do not want that. But again, solving just to keep your system safe and not caring about the task is easy. We can create some sort of backup operator. This can be another MPC. It can be a simple put all the emergency brakes in, scram your reaction, do whatever they want. Cute. This backup operator can be quite literally anything. I'm going to show you an example later. I'm going to tell you what it did there. This is going to create some sort of backup action. This does not care about the task at all. It only cares about our safety constraints. Keep the system in some sort of safe state, get the car into a safe position, get the robot to stand upright and do nothing. Whatever. Simple. It's going to do that for as long as it takes to return the system into a safe state. What a safe state is needs to be defined beforehand. For example, again, stopped car. At this point, everything will start over. Our system is safe. Our reinforcement learning model can do something again. It might mess up again. That's the trial and error part. But this action here never got applied to the environment. That's the crucial part. We never acted in an unsafe way, actually. All of this is happening internally. And that is how we build an architecture that keeps the system safe while still learning, because we still have this bonking of our reinforcement learning model. It still knows that it messed up, but nobody got hurt. That's the good part. I have this in here. This is the actual scientific way of how this architecture would be described. I have this here because that is actually the thing that they did at the University of Lübeck in the research group I was a part of. This was used for model cars, where some obstacles were placed into the path of the car, and the car just drove around them beautifully without the reinforcement learning agent having any say in the decision, because the system doesn't allow it to make those kinds of decisions. It doesn't allow it to drive into a wall. That is where all of those car analogies I've been using in this talk came from, because at the University of Lübeck they do a lot of research with those cars. My work in all of this was actually applying this to some sort of learning scenario, because the reinforcement learning agent used on the cars wasn't learning at the time. It was just some sort of thing that they put in there. For my research, I focused on something much simpler, because I was a bachelor student back then. I didn't know a lot of things, and I was in academia, so it didn't need to be a very useful application. Those of you familiar with reinforcement learning will know this one. This is a staple. The Cartpole model is used as a bunch of as a benchmarking tool for a lot of reinforcement learning agents and different algorithms. That's why I also used it here. It is quite simple. The task is to keep this pole upright on a car that you can move to the left and to the right. And if the pole falls, well, you lost. In the example I'm going to describe here, the pole falling will be some sort of whatever critical thing. Maybe there's a self-destruct button right here. Something along those lines. We have the equations for that thing. Again, you don't need to understand all of these equations. What I want to point out is that this is from the source, the correct equations for the dynamics of the Cartpole system. That paper is a page-for-page refusion of another paper, and it is quite literally, hi, these are the equations that this guy put out. They're wrong. These are the right ones. It's 4 pages long. It's a delight to read. It's my favorite source in all of this, because he is so petty. I absolutely adore it. Okay, we also have a reward signal. We make it really easy for ourselves. The reward is just always 1, and well, the pole is upright, and it will be 0 if it isn't. It will also be 0 when our MPC tells it that it messed up. Pretty easy. Not much to do here. Some of you may ask yourself now, wait, this seems to be a very easy task to describe mathematically, and you would be perfectly correct. It does not make sense to apply this architecture here. This is purely for academic research and to see that we can apply this architecture to something and create a reinforcement learning agent that actually learns something. So, yeah, this is not useful in the real world, but it demonstrates our architecture really well. And I am going to show you this now. Because, again, I did that as a research thing. I need to figure out if this... Wonderful. Where is the window going to appear now? Perfect. You see our little Cartpole right here. I hope you can all adequately see that. And you will see a bunch of outputs here. I am not a very good programmer. So this, all of this output is really garbled, because I was in a hurry when I wrote this, and it is not very beautiful. But it does work. You will see here that the reinforcement learning training steps will go up periodically, and then they will stop, and this is going to say MPC controlled. This is whenever the reinforcement learning agent made some input that will lead to the pole falling in the future. You will also notice that it doesn't fall, ever. This simulation can run forever without the pole ever reaching the ground. Whatever system you put in there, you can design the worst possible agent for the system, it will not make the pole fall, because our Model Predictive Control supervisor is going to prevent that. This is really fun. It is going to do a lot of things here. You will also notice that it starts intervening very early. The pole has barely started tilting. That is because you want it to intervene pretty early on. You want to keep some margins of error for the thing to have some calculations. Actually, I ran into floating point errors when I wrote this. That was the amount of precision that the system is dealing with in the future, because floating point errors are enough to lead to an unsafe state here. That is why you put those extra tight constraints on it in order for it to prevent falling. Theoretically, this should lead to the system learning faster, because the reinforcement learning agent will notice at an earlier time when it messed up. theoretically. Does not happen in this example, because it is a very simple example and it is not sufficient to supply that sort of knowledge to the system. I will not go into detail on that. I have some theories about that. I did not get to test that in my research, sadly. You will also notice that this says 2 hours and 10 minutes. That is a long time. You will also notice that this one barely goes up. Well, that is an issue. We're going to get to that issue in a second. You will see that this is not a well-written script at this point. I will have to kill that for a lot of times before it actually stops. I was right here. Beautiful. Those are the results. Those of you familiar with reinforcement learning, benchmarking will also know this sort of graph. It is your reward curve. The reward in this experiment is just, we put it into a test environment and see how long it takes for the pole to fall. It is capped at 2000 because otherwise it's going to take forever to test. We see our system learned just fine. It learned that some sort of control configuration that will keep the pole upright for 2000 steps, which I defined in this experiment as good. This system works. The red curve is our model predictive control interventions in the training period preceding these evaluation periods. Those are always 250 training steps. Well, those are a lot of model predictive control interventions. But, as we would expect, they go down over time. Why are there still some here at the end? Because the system keeps training. It keeps trying to change itself. It keeps trying to do something new, which means it will get worse. From time to time, you see it here, it does get worse at some points. Wonderful. We have created a system that learns. We have created a system that learns without ever letting the pole fall. This was a huge success when I had this graph. I will show you for comparison a graph without the model predictive control supervisor. In this one, it was allowed to fall. It still learns. It looks quite similar. It is actually slightly faster to do it without it, from a training step perspective. It is also very much faster to do it without the the MPC supervisor from a time perspective. It takes about 5 times as long to train this. Do we care about that in safety critical applications? No, we don't, because again, we do not want to kill somebody. Is it good? No, it's not. But that is the price that we do have to pay. I'm going to look with you into this timing a bit more. This is the timing of every single step taken in that simulation. You will notice these specific sort of lines here in the green ones. Those are the evaluation periods. They take as much time as it, takes to go through the 2000 steps here, or the whatever amount of steps down there. In blue, you have the actual training steps. Those take roughly the same amount. Those small little outliers are just something that the library does sometimes. Those appear in the reference runs as well. I do not know why they happen. They just do. And the red ones are the interesting ones. Those are the model predictive control interventions and the amount of time that the backup operator took to restabilize the system. That takes a lot of time. It usually takes around 8 seconds, I think is the... No, I think the baseline is around 6 seconds here somewhere. On average. It goes up to 45, and it goes down to like half a second at some points. That is depending on how badly the system messed up, how badly your pole is currently swinging, whatever the reinforcement learning agent did at that point. I have no way of knowing. But again, nothing ever fell. That is the whole point of this. But it takes a long, long, long time. And the Cartpole model is very, very simple. I applied this architecture also to the kinematic bicycle model in a different simulation. I let that one train for around 23 hours without a significant improvement in the performance of the reinforcement learning model. That is simply because it takes forever to compute those steps. Because the model is really complex. This case, the model is simpler. We can do that in an academic context. Wonderful. So what did we achieve now? We created an architecture that has an interplay between model predictive control and reinforcement learning that is reliable, provably correct when given an accurate system model. It is adaptable to different tasks because that is the job of the reinforcement learning. It does not kill anybody. That's the job of the MPC. It is still insanely computationally expensive, but again, we don't really care about that in safety critical applications. And it still needs a mathematical model of your environment. That is correct. It doesn't need that. That is something that we need to create. We need to tell it where the walls are, where the self-destruct button is, how everything works around it in a mathematical way. At least all the things that we care about for safety. It also needs a mathematical system model. I marked this one as neutral because for robotics applications, we have those anyway. Kinematic models of your robots are the basis of all robot development. You can't do forward kinematics without a model of your system, so I don't think that this one should be a huge issue. So yeah, we created an architecture that does not kill anybody. In the end, the only way to actually prevent the robot uprising is obviously to ban red LEDs in robots because they can't turn evil if they can't have red eyes. Wonderful, thank you very much. You can reach me here, you can also talk to me. I am a bit early, so we will have time for questions. If you have any, feel free. Sure.
So I understand it. You said that it predicts what will be the next input, and then you said it also predicts what it's going to give as output. So I just have a fished understanding here. Is it so that its output is always also different? It doesn't have that when I get this input, it's not rule based. So that's the learning. It doesn't know itself and it's only predicting too?
The model predictive control does not learn. That is a purely mathematical model. It's going to, this is an optimization problem. It's going to calculate what is the optimal control input to achieve its goal. It's going to do that over this prediction horizon. That is a bit further into the details and the math, how it works. What it's going to do is it's going to say, I will apply this control input to the system at this step. That is going to change our output this way, or I think it will do this. The model predicts that it will do this to our output. In the next time step, I'm going to apply this. That will change it that way. The next one, I will apply this. That will change it that way. And it's going to try to optimize this predicted output for our reference trajectory in this example in order to closely match it over our prediction horizon up here.
Okay. Okay, thanks for that. And the other question is, just because you were speaking about safety and maybe you heard about the plane crash in India where lots of people got killed, Boeing. So I would like to know that in generative AI we hear of confabulations or hallucinations, but why is it that with math-based models we have errors? Couldn't we do something with math which is always fail-safe?
That is a good question, actually. And I will take this slide to explain it. In planes, for example, we do have a general model of how aviation works. We have a general model of how planes mathematically work. We don't have a model of everything inside of the train. Our system model is not very accurate for planes. Our environment model, how the air changes around it, that is like chaotic airflow, we don't have a model for that. We can't describe those mathematically at all. So we don't have an accurate environment model. So we can't apply this sort of control strategy to airplanes. This is applicable for any system with a well-known system dynamics in environments that we can describe, at least the safety parts. We can't do that for planes. This is the reason that this does not really work very well for those kinds of applications. That is correct.
Okay, thanks.
Wonderful.
In that case, follow-up question: to what extent is the first flight of the A320 that ended up in a forest in Alsace a known example how these things play out?
I have no idea what that is.
He doesn't know what that case is.
Okay. Way back when old white men like me were younger, the A320 got a computer got a fly-by-wire system, and they wanted to show off the A320 by a low approach in a small airfield in Alsace, and they wanted to go. The pilot wanted to go around, and the engines didn't respond fast enough, so they ended up in the forest and killed a few people, and the career of the pilot.
I don't know if that was a model predictive control algorithm running on that. I would assume that that is also because of model inconsistencies at that point, because you can't model everything that a plane is exposed to.
What happens if the math is a matter of the time to do the math is a matter of the model too? Because when this environment changes quicker, then it can compute. What happens then?
That is a real-time constraint on the system. That is correct. That is an active research topic going on currently. This architecture, as it is currently done in research, all of this is active research, is currently slower than real-time for a lot of applications. It is actually faster than real-time on a beefy system enough for the Cartpole. It is also fast enough for the cars, for the model cars. It is, this architecture or something similar has been applied to a model of a human with all of the kinematics that our limbs have. That runs about 10 times slower than real-time. That is the current state of research. And that is just a compute problem or an optimization problem. There is some research going into doing more efficient MPC algorithms. That is all out of scope for this talk. It is a very active field of research.
Thank you.
I hope that answers your question. Wonderful. Okay. Then I thank you very much for coming.